So today I'm going to talk about a result that is a product of a conference, specifically the Agnes conference in the Agnes Summer School on Intersection Theory of 2003, where Samir Canning and Emily Peter led a project with myself, Xiaoqi Mok, and Amy Lee, who are here in the audience, and Richard Abukar and Carolina Tamborini. And the result is about constructing non-tautological cycles in M-star GM2M. So the first part of the talk is going to try to make sense of this title. So I'm going to tell you what a tautological ring is, where does it live, so particular the Chow ring, and what are these non-tautological cycles. So let's start with the Chow groups. We will construct the Chow groups and the Chow ring, which is a ring containing the tautological rings. So our Chow groups are denoted by CHK, and this is so these can be defined also with integral coefficients, but we're going to work with rational coefficients only today. And these are the k-dimensional subvarieties for X. And then I'm going to assume X smooth. X is smooth variety. Over rational equivalence. Rational equivalence means essentially that two things are equivalent if this is my X and if two three-dimensional subvarieties, those two are rationally equivalent if I can somehow find a subspace of X that has dimension one more, where these two are rational, where these two are linearly equivalent divisors, which means they are the zeros and poles of my PP1. Now we can index these guys by codimension, so we can define C H upper K of X as the dimension of X minus K Chow group. And these are going to be summed into a graded ring. We have at the sum, the Chow ring is going to be defined as the sum for k greater equal than 0 of these Chow groups indexed by codimension. Now I've told you what the elements are and what the addition is, but I haven't told you what the multiplication is. And this is the reason why you care so much about Chow rings is specifically because the intersection is basically because the multiplication is counting intersection. And ideally, so I'm going to say multiplication is the intersection. And I put this in quote with parentheses. And I put this in quote because this is only true when the intersection is transverse. This is not quite true in other cases, but there is, the good thing is there is an intersection product that keeps track. That is exactly the product of the ring that keeps track of intersections. And now this reminds you of cohomology. That is because the two are connected. In fact, if you look Chow rings on Wikipedia, the first sentence is the Chow ring is the algebra geometric version of cohomology. And in fact, they are connected via a map called the cycle map. So there's a web. So there's a map called the cycle map from the Chow ring of X to be even dimensional, even degree parts of X, sending a subvariety to a cycle. In particular, we are interested in what happens when we pick X to be MG, and today we're specifically going to be interested in what happens when we pick X to be MG to N without the bar. But in order to start telling you about that space, I have to start with M to G and with X M bar G to N. And now I'm going to take advantage of the fact that many speakers already explained what MG and G and bar is. I'm just going to say it out loud. This is the moduli space of stable curves of genus G with 2 M marked points. Please feel free to ask questions.
Why is it 2M?
It is 2M because we will need it in the proof.
Okay, so you just want to use even.
Yeah, I mean, yes, because we will construct the locus. We will construct a locus there that comes from dialectic locus, and so we'll fix. Yeah.
Okay.
It will be clear later.
Okay.
But we need even.
Okay.
So in particular, we now have maps of Chow rings that are induced by maps in the moduli space of curves. So we have the gluing map. That picks a curve. I mean, in fact, it picks two curves. One of genus G1 and one of genus G2. With series of marked points on them. And so we start with these two different curves and we glue them along the last point. And so we obtain the following curve. Which in particular gives us a map of Chow rings. In fact, sorry, of Chow groups. In fact, this does not preserve the product operation. So maps of Chow groups. And so this goes from the product MG1 G1 MG2 and 2 plus 1 to the child of D1 plus D2 and 1 plus N2. Similarly, another kind of gluing map that starts with a curve with at least 2 marked points and genus G, we can take the last 2 points and glue them together. This will give us a map, a curve that looks something like this. And this will define a map of Chow rings, Chow groups, from G n plus 2 to Chow of N G plus 1. I'm left with one extra map that, I mean, there's many maps, but these are the ones that we are interested in to construct the tautological grid. And then there's the forgetful map. starts with a curve with a series of marked points and forgets some of them. And this gives us a map of child groups from the child group M G M plus K bar to the child of M G M bar. Okay, so I've told you all the maps that we need to define the topological ring.
Sorry, could you say again where the second map comes from? The one that's lower on the top row?
This one?
Yeah, just quickly.
So I am taking a curve of genus G. And on this, I'm remembering multiple marked points. In this case, I can have 1, 2, 3, 4, 5 marked points. I'm going to take the last 2 points and I'm going to glue them together. And so this is going to be a new node, and I'm still going to remember point 1, 2, and 3. Okay, and so now I'm going to define the topological ring R star of M, G, and bar. Actually, let me define this here so that I can keep pointing at it while I tell you. So R star, R has a star, and GM bar. This is a subring of the child ring. And this is the smallest subring closed with respect to the push forward. So these, I'm going to refer to these maps as the push forward of the gluing map and the forgetful map. With respect to the push forward, gluing map, and the forgetful map. Moreover, I'm going to ask for this ring to contain some special classes, gamma 1, gamma n, that for who is familiar with Chern classes, these are the first Chern class of line bundle L. So phi I is the first Chern class of line bundle L, where L is restricted to the point C P1 Pm is going to be equal to the cotangent 1 so this ring, let me forget for a second about R and let me talk about the localization sequence, which is a very powerful tool that we have when working with child rings that we don't have when working with cohomology. So the localization sequence. This is a sequence that connects the child ring of my variety X with the child ring of an open contained in X. And it is the following. So we have this short exact, sorry, it's not short, it's just exact sequence of roots again from the child of X minus U to the child of X to for the child of u to 0. In this case, we want to take x equals mgn bar and u equal mgn. So with this hypothesis, by using the localization sequence, we can define a subring of the child mgn without the bar by looking at what happens via the image of this map, which is also a push forward of the emergence u in x. In particular, we define our upper star of mgn as the image via the push forward of the tautological ring in mgn bar. So far, I haven't told you what these shards are in cohomology, but I have promised you a non-tautological cycle in the cohomology ring. And these, so let me tell you, yes. Yes.
The maps of the push forward maps, they preserve the lower degrees, right, rather than the upper degree. So they preserve dimension rather than co-dimension.
Correct.
So perhaps just to make it clear.
Yes.
Okay.
I have not introduced this notation here, but we're just taking the sum of all of the child groups indexed by dimension. So child lower k. Yes.
Can you lower the voice?
So I'm now going to define RH, other star, which is contained in other star, which is a subring of the cohomology defined.
That map is not the push forward. I thought the push forward.
It's a pullback. Thank you. You should know that I discussed this before and I got confused multiple times. Thank you for catching that. Okay, so now I'm going to find this guy as the image. Get the cycle map of RH, sorry, of R upward star of MGN bar. So it's the subring of classes that come from algebraic cycles, from tautological algebraic cycles in the child. And similarly, we can define RH upward star of MGN as the image via the cycle map of R up star of MGN.
What does the R stand for? It's tautological rings. So T would be much more natural.
That is a good question. I never asked that myself. I don't have an answer, but
T star would be the cotangent. So it's
Yeah.
And R is for ring angle.
yeah.
That's always annoying in presentation, I don't know why.
But honestly, I'm not even sure. So sometimes the chow is denoted by A, and I'm not sure. If I'm very interested in knowing where the A comes from as well.
Oh no, oh no.
Ah,
French.
Thank you.
So that makes
I don't know.
for ring research.
Yeah.
Okay, so now that I have to find all of these questions, sorry, now that I have to find all of these strings, I can ask myself lots of questions that in general are not easy to answer. So I can ask myself, when is it that H equals R? So sometimes the answer is relatively easy. If, for example, if we have odd cohomology, and these two are never going to be the same. There are some cases where the answer is yes. Specifically, we have an even harder question that we can answer. That is, when is the Chow ring? When is the tautological ring equal to Chow ring? So I think these are questions that are answered for a finite number of genuses. And then, sorry, these are questions that are answered for infinitely many. The answer is yes for only a finite number of genuses. There is another question that somehow is related to these two, which is a question that I want to answer today, which is, can I construct algebraic cycles which is, can I construct things that are in the image via the cycle map of the Chow ring inside the cohomology ring that are non-tautological. And in particular, I want to construct some cycle in H upper star. And this will answer also my original question about the Chow ring, if I pick an algebraic cycle.
So this is sort of the refined question. You don't want necessarily, I mean, whatever cycle you would construct would not be in the Chow ring of in the tautological ring in the Chow ring, but also when you take the image, it's still not in the
Exactly.
Ah, okay.
Yes.
Okay, just to be on the safe side.
And let me tell you a little bit of history about this, because this is a question that took longer to answer. So the first answer we get it from in 2003 from Graber and Van der Pande. That construct a cycle for G equals 2 and N equals 20. And this works for both. Well, these questions can be asked both for MGN bar and MGN. And this cycle here is a non-tautological cycle in H upper star of MGN bar that restricts to a non-tautological cycle still in H upper star MG. Another result that gives us an answer, like an explicit algebraic cycle that's constructed, is from Bantel, which gives us infinitely many G's and N's for the case of NG and bar, but only a finite number of them for MGN. Is it visible or should for MGN? And these are exactly when we ask G plus N to be exactly equal to 12 and N equal to N. And yes, we're going to see, and then our results also offer another answer to this question, which is in infinitely many cases for GM without the bar. So hopefully, during the rest of the talk, I will manage to tell you what this cycle look like, and give you a sense of how the proof works, to prove that these are non-tautological. So I'm going to find a locus inside completely different, not completely, it's a different space that is not MGN. And this is the space of the moduli space of admissible covers, admissible double covers, genus G, genus H, up to M, as the moduli space of objects that have this form. And I'm going to draw pictures first, and then I'm going to write all their parts. So I'm going to start with a map from curve C. To curve D. Where C and D are stable and nodal. Of genus G and H respectively. And the map F is going to be a double column. It's going to be a 2-to-1 map. I am requiring that nodes of these maps get sent to node. And then I'm going to mark some points. I'm going to mark the ramification point xi. So x1, xr are ramified. And these are F. going to mark a series of points, yi, so y1, y2, y3, and y4. Such that the involution defined by this 2-to-1 cover swaps. Swaps them pairwise. So y 2i minus 1 and y 2i are swapped by this involution. I'm going to ask more things, but let me first write down all of the things that we are asking explicitly. So we are asking for a triple F from C to D, Xi's and Yi's, such that F double cover, C D stable nodal curves of these G and H respectively. I'm going to ask the Xi's to be ramified points and the y2i minus 1, y2i to be swapped by involution. I'm also going to ask that F sends nodes to nodes. This is, yes, these are all the requirements for objects, for the object in this moduli space. Now I'm going to have to define a map from this moduli space to my moduli space of stable curves. So I'm going to start so this is the locus. B bar of G to H 0 to M. And feel free to ignore the 0, because for the purpose of this talk, it will play no role. Just know that the map that I'm about to define can choose to remember some points of some of the ramified points. And if you remember n of them, you put an n here. But for today, we'll not care. I'm just using it to respect.
Do we view D as stable with these markings of the images of the ramification points?
Yes. This is a good point because we are about to forget those points. And so we'll need to do some manipulation. So we will start from, so we want to construct a map from the admissible double cover from genus H to genus G with 2 M marked points. And I'm going to go to M 2M far. So we're going to start with our curve Sorry, with not with the curve, with the map. Or over here we are. Over xi's and what are yi's? Sorry, xi's and yi's. This is y2, this is y1, y3 and y4. Right? Yes. And so what we do is we'll just start by simply forgetting the xi's. And sorry, we forget the xi's and we pick the source curve. In particular, we are mapping this to the curve. Y. So we're still remembering y1, y2, y3, y4. And this is why the 2m comes into play. It's, now we have a problem because this is not stable anymore. So these rational bridges don't have marked points, so they have automorphism. And so what we're going to do is we're stabilizing the curve, and we're going to get something that looks like this. And the image, so this is going to be my map phi 0, which the 0 is going to be this one. And again, this is just to keep the notation consistent with the one of the paper. And yeah. So I'm going to define d bar g h 0 to m as the image via phi 0 of the moduli space of a principal color. A principal double color. To m. Now, finally, I am ready to state the theorem. That's a light again. And we define B without the bar, G to H, 0 to M, to be the image via excision. Sorry, via the pullback of the inclusion. Of MGN without the bar into MGN bar of B bar to the H. I mean, is it visible if I leave it like that? With all of these definitions in place, I'm finally ready to state the theorem. So if you are familiar with the work of Van Zel, and what Claudia was talking about yesterday, this is the locus that he starts with to construct the non-tautological class in his paper with H equals 1. So it's the bielliptic locus. And in fact, the strategy is our strategy is a direct generalization of what Anselm does in his paper. So theorem. If H let T be greater or equal than 2 H, and then let K be G minus 2H plus M minus 1. Then assume so MGN bar is smooth and proper, and so it admits a Hodge connect decomposition. And so we're asking of the group H, 3H minus P plus K on 0 of N HK bar to be non-zero. So if we assume this hypothesis, then our cycle B 0 to H 0 to M is non-tautological. And so this is a theorem, but before I dive in what goes through proof this theorem, let me tell you in which cases this hypothesis is satisfied.
Question. So it's not tautological in the homology of the open?
Yes,
Okay.
it's not about, yes, sorry. And, the second proof that we are looking at is the dimension is 2 H minus 3 plus K of M G to M. Thank you. So the conditions for H, so 3H minus 3 plus K 0 and HK being different from 0. So if H is 1, then this is a known result. And we have that HK 0 of MG 1K is non-zero for K odd, and K is different from 13. And then if H equals 2. We have that this is a result of the paper. Then we have that k plus 3, 0 of m bar 2k. This is non-zero for k even and k greater or equal than 14. In particular, let me state the theorem in a nicer way, where we actually can see all of the G's and M's such that you can find in this way some tautological classes, not some non-tautological classes. So B to H zero M is non-tautological. Or so we are asking, I have it there, up there. So if we ask G plus N to be even, then we want to consider sorry. Let's do the other way around. So if we start with H equals 1, then we get that K, this implies that K equals G minus 2 plus M plus 1 equals G plus M.
Minus one, minus one.
And we want this to be odd. And G plus N to be even and different from 16. And G plus N greater or equal than 14. On the other hand, we can ask G plus M to be odd. In that case, we want to look at H equal 2. And our K becomes G minus 4 plus M 1. Sorry, this always had been a plus 1, which means this is a minus 3. And so in particular, we get that this is true for G greater or equal than 4, N greater or equal than 0, and G plus N greater or equal than 17. Which in particular allows us to compute infinitely many of these non-tautological cycles. In particular, an interesting consequence of this is if we pick M equals 0 for, let me make sure that I say the numbers right. For G greater than 16, we have non-tautological cycles in the homology of MG without the bar. And we know almost everything about whether or not NG can or cannot be can or cannot contain non-tautological classes. In fact, NG RH of NG equals H of NG. And this is, there's many mathematicians that contributed to this result for G smaller or equal to 9. And this strictly contained an H for G greater or equal to 16. And so there are still open a finite number of cases in between where we still don't know whether or not this inequality or that equality holds.
Are you willing to guess?
So I am not.
Okay.
But I'm pretty sure Samir Canning and Hannah Larson are working in the cases 10 and 11, and that is suspected to be tautological. But this, it also may be me misremembering. So
Okay.
Okay, so I think I have 10 minutes to tell you about the proof. Or did I just raise the theorem that I wanted to? Let me actually keep it on that, right? Try to rewrite. All right, so let me call B. That will be G. 0 to M. And we are assume that this is tautological. Then my goal is to reach a contradiction. In particular, I'm going to look at the map I, doing 2 copies of MHK bar. The appropriate number of points so that I get, as a result, a map of MG to M. Yes. And now I'm going to claim, I haven't told you about that, but pullback preserves a class B tautological. In particular, I'm going to look at what happens when I pull back B. Sorry. Let me take a step back before. This I is going to be defined in 2 minutes. Let me start by defining a different cycle, B bar. And this cycle B bar is going to be B bar GH 0 to M, our familiar, the familiar image of the admissible cover that we see before in MGM bar. Now we know that via the cycle map, B bar must. And let's assume that now this B bar being mapped to is mapped to B via this map, via the excision map. So chow of M via bar to chow of M N. And here we have the chow of the boundary of MGM. And we know that this cycle B gets mapped without the bar. And we are assuming that B is tautological. In particular, there's a tautological class here that maps to B. Let's call this T. So in particular, B bar must be equal to the tautological class that maps to B plus something that gets killed, which must be the boundary graph. So I'm going to call this guy D. And so before I start telling you about the I, yes, no, this is the right moment to tell you about the I. Sorry. So what I'm going to do now is I'm going to look at that equality over there. Pull back the I from R. Oh, gee. These guys, these and here should have been 2M. Then in particular, we get the equality I pull back at B bar equals I pull back at T plus I pull back. Oh. And the contradiction that I'm going to reach is I pull back at B bar. It's going to have as a non-trivial contribution is H 3H minus 3 plus K 0 of HK. But I go back at T and I go back at D have trivial contribution. Particular vector space. And this is the contradiction that we're going to reach. Van Zan does something similar, however, he does not look at the kinetic composition. He uses odd cohomology of M11 1 11 bar. But he has a similar strategy of reaching a contradiction that way. I think I'm not going to say anything more about it.